Let's be real. The word thermodynamics doesn't exactly inspire joy. It sounds like something whispered in the halls of suffering, alongside partial differential equations and quantum tunneling. You probably imagine boards filled with symbols, equations with more Greek letters than a frat party, and professors who smile when your brain breaks. But here's the truth. Thermodynamics isn't trying to ruin your day. In fact, it's one of the most practical and down-to-earth fields in all of science. Strip away the jargon and fancy math, and what you're left with is a very simple concept. Thermodynamics is the study of how heat and energy behave. That's it. No need for interdimensional thought spirals, just heat, energy, and how those two things move, change, and occasionally make your coffee go cold before you've even taken 2 sips. So no, you don't need to be a physicist to understand the basics. Maybe you're a student trying not to fail your next exam. Maybe you're just a curious human who's heard the word entropy one too many times and finally wants to know what it means. Or maybe you've always wondered why nothing in life ever seems to be 100% efficient. Not even your toaster. Whatever brought you here, this video is ready to guide you through the essentials of thermodynamics in a way that won't melt your brain, because no one deserves a thermal breakdown trying to understand thermal energy. Let's kick it off with the foundation of it all: energy. Before we can talk about thermodynamics, we need to talk about what energy actually is. Most people know it's important, but if you ask them to define it, you'd probably get a few long pauses and a nervous shrug. That's fair. Energy isn't exactly easy to pin down, but in the simplest terms, energy is the ability to do work. It's the fuel behind motion, heat, light, sound, and even life itself. Every breath you take, every beam of sunlight, every engine that turns a wheel, it all comes down to energy making something happen. Energy shows up in many forms. There's thermal energy, which we experience as heat. There's kinetic energy, the energy of movement. A car speeding down a highway, a baseball soaring through the air, even a falling apple. All of them are bundles of kinetic energy in action. Then there's potential energy, which is basically stored energy. A stretched rubber band, water behind a dam, or a rock perched on the edge of a cliff, all hold potential energy that's just waiting to be unleashed. We also have chemical energy, locked inside batteries, gasoline, and the food you eat. Break the right molecular bonds, and that energy gets released. And don't forget electrical energy, nuclear energy, and radiant energy, each with its own quirks and uses. But in thermodynamics, the spotlight usually goes to thermal energy and how it transfers from one place to another. A helpful way to think about energy is to imagine it as money. You can't create it out of thin air, and it doesn't just vanish into nothing, but you can transfer it, convert it, and spend it on different things. You can turn the chemical energy in a granola bar into motion by walking. You can convert electrical energy into light and heat by flipping a switch. But no matter how many times it changes hands, the total amount of energy stays the same. That's where the first law of thermodynamics comes in. Think of it as the universe's accounting department. It keeps meticulous track of every bit of energy and makes sure nothing gets lost or created out of nowhere. The first law is often summed up as, energy cannot be created or destroyed, only transformed. In science speak, it's usually written like this: du equals Q minus W, which just means the change in a system's internal energy equals the heat added to it minus the work it does on the outside world. Sounds fancy, but the meaning is simple. If energy goes into something, it either stays there or it leaves as heat or work. Let's break that down with something more familiar. Picture pouring gasoline into a car. That fuel contains chemical energy. When you start the engine, that energy gets converted into kinetic energy that moves the car, thermal energy that heats the engine, and even sound energy, the comforting rumble that tells you it's time to hit the road. Nothing disappears, and nothing appears out of thin air. The energy simply moves through different forms. If you follow the trail, you'll see every bit accounted for. This law is also why we don't have machines that run forever. Every engine loses some energy as heat. Batteries drain, systems degrade. Energy isn't vanishing, it's just escaping into forms that are harder to use. If someone ever tries to sell you a free energy machine or a perpetual motion device, you can confidently decline. The universe doesn't give out loopholes, and it definitely doesn't break its own laws for convenience. So now, we've established the most important rule of energy. The total amount always stays the same. But what about how energy behaves as it moves? That's where the second law of thermodynamics steps in. And this one has an attitude. If the first law of thermodynamics is all about keeping track of energy like a cosmic accountant, then the second law is more like the universe's messy roommate. It doesn't just care where energy goes, it cares how it goes. And the key idea is this: energy naturally flows toward greater disorder. This principle can be summed up by one big concept: entropy. Now, entropy might sound like a villain from a sci-fi movie, but it's really just a scientific word for things falling apart. Technically, entropy measures the amount of randomness or disorder in a system. The second law of thermodynamics tells us that in any natural process, the total entropy of a closed system will either stay the same or increase. It never decreases. The universe doesn't clean up after itself. This is why your hot coffee gets cold when left on the table. The heat energy in the coffee doesn't disappear, it just spreads out into the air. The molecules that were buzzing with thermal energy slowly settle down as that energy gets shared with everything nearby. That's entropy increasing. Energy is becoming more evenly distributed, more disordered, and less useful for doing work. You can't just wave a wand and have all that scattered energy return to your mug to reheat your drink. That would be reversing entropy, and the universe has a strict policy against that sort of thing. Think about a tidy room, everything in place, neat and organized. Now leave that room alone for a few days. No one has to actively mess it up. It will slowly get dusty, cluttered, and chaotic all on its own. That's entropy creeping in. You can clean the room, sure, but it takes work. And in doing that work, you're probably burning energy, sweating a little, maybe even swearing a bit, creating more entropy in the process. You can lower entropy in one spot, but it'll go up somewhere else to compensate. That's the deal. And this principle isn't just a quirky side note. It's one of the most important ideas in all of physics. The second law explains why no engine is 100% efficient, why your laptop heats up when it runs multiple tasks, why you get tired after doing something strenuous. In every case, some energy is always wasted as heat. It leaks out of the system, spreading into the surroundings in ways that can't be fully recovered. Even the best designed machines in the world must live with this. You can optimize all you want, but you'll never beat the second law. It's like trying to mop up the ocean with a napkin. It's noble, but pointless. One of the wildest implications of entropy is its relationship with time. In fact, entropy is the reason time moves forward. It gives us what scientists call the arrow of time. Events unfold in the direction of increasing disorder. That's why you remember the past but not the future. Why broken eggs don't unbreak. Why burnt toast stays burnt. The universe, at its core, is always heading from order to disorder. Now, you can fight entropy, but you'll never win. You can delay it, redirect it, even manage it, but you can't undo it. A refrigerator, for example, keeps your food cold by pushing heat out into your kitchen. It lowers entropy inside the fridge, but increases it outside. Net change, more entropy. And that's perfectly legal, thermodynamically speaking. So if the first law says energy sticks around no matter what, the second law adds a twist, that energy gets less useful over time. It spreads out. It loses its edge. It becomes harder to capture or control. That's entropy. That's thermodynamics being brutally honest. And it doesn't stop there. Things are about to get colder, literally. Because next, we'll look at the third law of thermodynamics and what happens when you push temperature so low that even atoms can't handle it. There's cold, there's freezing, and then there's absolute zero. The theoretical basement of the temperature scale, where even atoms call it quits. Absolute zero is exactly 0 Kelvin, or about minus 273.15 degrees Celsius. That number is the point at which the motion of particles completely stops. No shaking, no vibrating, not even a subtle wiggle. If you could somehow take an object to absolute zero, its atoms would essentially freeze in place. No energy left to move. It's the ultimate chill, a kind of cosmic do not disturb mode that nature doesn't casually allow. This idea forms the basis of the third law of thermodynamics, which states that as a system approaches absolute zero, its entropy, that measure of randomness or disorder we talked about earlier, also approaches zero. In other words, when you cool something down far enough, it doesn't just slow down, it becomes perfectly organized. Energy stops moving around, disorder fades, and what's left is stillness, so complete, it almost feels philosophical. It's like the universe pressing pause on its endless chaos. No surprises, no stray molecules zigzagging around, just absolute order. Of course, like most things that sound too neat and tidy, there's a catch. No one's ever actually reached absolute zero, and it's not because we haven't tried. Scientists have used advanced techniques like laser cooling and magnetic traps to slow atoms down to incredibly low temperatures, fractions of a degree above 0 Kelvin. We're talking billionths of a degree. That's unimaginably cold. Yet, despite our best efforts, we've never quite made it all the way. That's because there's always some leftover energy that refuses to leave the system entirely. It clings on, just enough to keep the temperature from hitting the theoretical floor. This matters more than you might think. As systems approach absolute zero, strange things begin to happen. Materials that normally resist the flow of electricity suddenly lose all electrical resistance. These are called superconductors, and they allow electricity to move through them with zero energy loss. In the everyday world, that's impossible, but in the ultra-cold world, near absolute zero, it's very real and incredibly useful. Scientists have also observed that atoms begin to behave more like waves than particles when cooled to near neglo temperatures. Entire groups of atoms can act as one, forming what's known as a Bose-Einstein condensate, a state of matter so weird it makes plasma look basic. This is where thermodynamics starts to overlap with quantum physics, and the results are nothing short of mind-bending. You go from tracking heat and energy flows to watching matter behave like a single quantum object. This is the realm of uncertainty, probability fields, and things that don't quite make sense until you accept that nothing makes sense at that scale. It's a strange crossover episode where thermodynamic order meets quantum weirdness. So, what does the third law really tell us? It reminds us that while the universe has a lower limit on temperature, we're probably never going to stand right on top of it. We can get close, painfully close, but never quite reach the finish line. Still, approaching that limit teaches us a lot. We've covered the first, second, and third laws of thermodynamics, but did you know that thermodynamics also has a zeroth law? Yes, zeroth. Like someone realized they forgot to number the first law and decided to sneak in a prequel. Despite the name, the zeroth law is actually pretty foundational. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In plain English, if object A is the same temperature as object B, and object B is the same temperature as object C, then A and C are also at the same temperature. It sounds obvious, almost painfully simple, but this rule is what allows the very concept of temperature to make any sense in the first place. Thermometers exist because of the zeroth law. You place a thermometer in contact with something, wait until it stops changing, and boom, that means the temperature and the object are at the same temperature. This law underpins the whole idea that thermal equilibrium is a transitive relationship, and it's why we can measure heat at all. So, while the zeroth law might not sound as flashy as entropy or absolute zero, it sets the stage. Without it, we couldn't even begin to define what temperature means, or how heat behaves from one object to another. With that foundation in place, let's now take a peek at one of the most misunderstood ideas in the field, what it really means when people talk about closed systems and equilibrium. Spoiler, it's not as boring as it sounds. A system in thermodynamics is just the part of the universe you're paying attention to. It could be a pot of soup, a jet engine, or the Earth itself. Everything outside that system is called the surroundings. Once you define the boundary, you can start tracking how energy and matter move. In an open system, both energy and matter can move in and out. Your body is a good example. You take in food, water, and oxygen and release heat and waste. That's an open system doing its thing. A closed system allows energy to move in or out, but not matter. Think of a sealed pressure cooker. Heat gets in, pressure builds, but nothing leaks out. If it's working, you're only tracking how the energy moves, not any escape of the physical ingredients. An isolated system doesn't allow anything in or out. No matter, no energy. These are rare in real life, but a good approximation might be a well-insulated thermos bottle over a short time. In theory, the universe itself is one massive isolated system. If that hurts your brain, don't worry. It's hurting mine too. Now let's talk about equilibrium. That just means everything inside the system has balanced out. The temperatures match, the pressure is steady, and energy isn't flowing anymore. It's like when your coffee finally cools to room temperature. Nothing exciting is happening, and thermodynamics calls that peace. But here's the fun twist. Systems tend to move toward equilibrium. It's what the second law demands. So no matter how wild things start out, thermodynamics always pushes for calm, eventually. We've talked about the 3 laws of thermodynamics, how they sneak into everyday life, and even untangled some of the most misunderstood ideas in the field. So now, let's wrap this up by answering the question that's probably still lingering in the back of your mind. Why does thermodynamics matter so much? The short answer is, it quietly runs everything. From the chemical reactions happening inside your cells to the engines powering rockets into space. Thermodynamics sets the boundaries for how energy behaves. It tells us what's possible, what's efficient, and where the energy leaks out when things don't go as planned. Every device that moves, heats up, cools down, or converts energy owes its function to thermodynamic principles. Power plants, smartphones, spacecraft, refrigerators, even your morning coffee, they're all obeying the same rules. For engineers, thermodynamics isn't optional. If you don't know where the energy is going, how much is being wasted, or whether your design will accidentally double as a portable oven, you're not building anything reliable. You're just guessing with expensive materials. In science, these laws go deep. They help us understand the life cycles of stars, how black holes radiate energy, and even how the universe might eventually fade into a cold, quiet stretch of maximum entropy. The laws don't just describe how energy behaves. They draw the line between what's real and what belongs in a sci-fi novel. You can't build a machine that runs forever. You can't rewind time, and unfortunately, your fries will never stay hot long enough. Thermodynamics even shows up outside physics. Biologists use it to study metabolism and energy flow in ecosystems. Economists borrow the idea of systems balancing inputs and outputs. Once you see how energy shapes everything, it's hard to unsee it. It's in your tea kettle, your sweaty workout, and the way your laptop wheezes under pressure. So no, thermodynamics isn't flashy. It doesn't bend time or break atoms, but it's one of the most powerful scientific ideas we've ever discovered. It explains how the universe works, and more importantly, why it can't work any other way. Thanks for sticking around until the end. If you learned something new, or at least didn't fall asleep, go ahead and hit that like button, subscribe for more science that doesn't require a PhD to enjoy, and tap the bell so you never miss a weird fact or a mind-bending breakdown. Thermodynamics may be done for now, but we've got plenty more heat coming your way. Catch you in the next one.